Here is the next example. In this example, we're still doing the DC analysis, but the difference is it's a PNP transistor. How do I know? The arrow is going in. If arrow is coming out, then that's NPN. If arrow is going in, that's PNP. The arrow is always on the emitter side. Okay, so do not confuse with my previous circuit, because the previous circuit I had emitter down here, collector up there. I can show you my previous circuit. It's going to be look like here. You can see my emitter is down here and collector is up there and the base is right here. But what I'm doing here, I just switched, and the arrow indicates that the current is going in. So basically IE current is going into the transistor, IC is going out, IB is going out. So this IE equal to IB plus IC. It is valid no matter what, whether it is in active mode of operation or saturation mode of operation, or if it is a NPN transistor or PNP transistor. And beta equal to IC over IB. This is valid for NPN or PNP transistor, but it is valid only in it is valid for active mode of operation or saturation mode of operation, both. But at the same time, beta value will change if it is in saturation mode. Okay, now same thing with alpha equal to IC over IE. You need to remember these three equations all the time. Now I'm going to start solving this example by assuming this transistor is working in active mode of operation. Active mode of operation, that means this EB junction is always forward biased, then CB junction is always reverse biased. Then only it's going to be in active mode of operation. Now here, to assume the active mode, the current is going to come down. Okay, so I'm assuming this is the current direction. That's where I'm going. Going to write down the KVL equation through this path or across this path. So minus 10 plus 5k times IE plus, so here since the current is coming down, this is the forward bias, the voltage must be 0.7. So here emitter is higher potential than the base, 0.7 volts. So plus 0.7 plus 100k times IB equal to 0. That is the KVL equation. So I'm going to substitute IE equal to alpha, IB equal to this equation beta, and then I'll solve for the circuit. Alpha, beta value is a big number. It's always given by the manufacturer. Big in the sense it's always between 50 to 200. So here I'm taking that value, or the problem, the questionnaire gave us the beta value as 100. So based on that, alpha must be beta over beta plus 1. So that value is 100 over 100 plus 1, which is 0.99. So alpha equal to 0.99. So here what I did, I applied KVL equation along that path. So here is the KVL equation I end up with, and I substituted IE equal to IC over alpha and IB equal to IC over beta. Okay, then I solve the equation. This is the given, after solving the equation, after substitution, I end up with finding the IC value as 1.53 milliampere. So IC is right here, that value is 1.53 milliampere. So based on that, can I find VC here? So VC minus of minus 10 equal to 5k times 1.53 milli. So that must be, this must be 7.65 volt. So VC must be, if I bring this minus of minus 10, which is positive 10, if I take it to the other side, it must be negative 2.35 volt. That is the voltage at point C. Now I'm going to find VE in this circuit. So VE equal to so to find VE, what I did, 10 minus VE. So 10 minus VE equal to 5k times IE. IE is the current passing through it. So IE, I found IC over alpha, which is 1.545 milliampere. So I substituted that value, end up with 10 minus 7.25 volt. So I end up with VE equal to 2.27 volt. Now what is VEC? So as long as VEC is greater than 0.3 volt, that is in active mode of operation. Looks like I have that value. I have VE equal to 2.27. So VE equal VE minus VC equal to VCA VEC. So I have VE equal to 2.27 volt and VC equal to minus 2.35 volt. So definitely this value is greater than 0.3 volt. So this transistor is working in active mode of operation. Thank you. I'll stop this video here, and the next video probably I'm going to solve a cascade connection. Thank you.